Alright, in our continuing series on Chapter 4, we today tackle Section 4.4, Prime Factorization. We're going to be looking at GCF, LCM, prime numbers, and monomials as well. So today's question is, how do we find the GCF and LCM of integers and monomials? The integers part is something you should have done back in pre-algebra or algebra 1. They're going to involve something like factor trees, which it's hard to draw on the screen, but hopefully you guys can remember how to do it, and I'll show you how to do them in class. And we'll be adding monomials, so we'll have some letters too. But don't be intimidated by them, because it's actually easier with the letters than it is with the numbers. So first we want to talk about prime numbers. A prime number is an integer greater than 1 whose only positive integral factors are 1 and itself. So 2 is a prime number because the only factors of 2 are 1 and 2. 3 is a prime number because the only factors are 1 and 3. 4 is not a prime number because along with 1 and 4, 2 is also a factor. So prime numbers, numbers that are only divisible by 1 and itself. And remember, it has to be greater than 1. So technically 1 is not a prime number. To factor a number over a set of numbers, write it as a product of numbers chosen from that set called the factor set. This is what you might have learned as part of the factor tree, where you put a number on the top and you divide it by prime numbers in order to reduce it to another prime number. And this is the process we call prime factorization. The prime factorization of any positive integer, write the integer as a product of primes. If a prime factor occurs more than once, use an exponent. Example 1. Find the prime factorization of 924. So I'm going to first do it the easy way, using, well, easier for me on my computer. Then I'll show you the factor tree that you might have done back in previous math classes. So what you want to do is look for prime factors of 924. Well, the easiest prime factor to look for is 2, because if it's an even number, you can divide by 2. So if you divide 924 by 2, you get 462. So you rewrite 924 equals 2 times 462. Now we deal with the 462, and again an even number, so you want to split that into 2 and 231. Well, not an even number anymore, so what do you divide by? I don't know if you guys know the divisibility rules, which I'll probably have to go over in class, but if you look at the numbers 2 plus 3 plus 1, they add up to 6. If the sum of the digits of a number are a multiple of 3, then it is divisible by 3. So it turns out 231 is 3 times 77, and 77 you could probably figure out as 7 times 11. So the prime factorization of 924 is 2 squared, because you write the 2's as an exponent, times 3 times 7 times 11. And that is the answer. Now, the prime factor tree, which you've probably done, I'm only going to do it for this slide because it's a pain to do on PowerPoint, but it's not that big of a deal on paper. So you can do it this way. So 924, we're looking at the same number. So we know it's even, so we have a 2. And what's left is 462. 462 is 2 times 231. 231 is 3 times 77. 77 is 7 times 11. So we get the same answer. 2 squared times 3 times 7 times 11. And for many of you, visually, this might be an easier way to do it. It doesn't matter to me. I could care less which way you do it as long as you come up with the right answer. But that's prime factorization. You're going to keep dividing until these numbers here you cannot divide anymore because they're prime. The greatest common factor and the least common multiple. The greatest common factor, or GCF, of 2 or more integers is the greatest integer that is the factor of each. The least common multiple, or LCM, of 2 or more integers is the smallest positive integer having each as a factor. So, again, these should be terms you learned in pre-algebra and algebra 1, and we'll see how this works mathematically right now. When you are given 2 or more integers, you can use their prime factorizations to find their GCF and LCM. So, you can use prime factors, you can use factor trees. Even if the numbers may be negative, the GCF and LCM are always positive numbers. So in a rare case, you might be asked, what's the greatest common factor between negative 12 and negative 18? The answer is always going to be a positive number. In this case, it'll be 6. Same with the least common multiple. They're always positive numbers. Let's go to example 2. Find the greatest common factor and least common multiple of 20 and 28. So we need to do the prime factorization for both. Go ahead and you can try that yourself, and then we'll do the next step together. The prime factors of 20 are 2 times 2 times 5, or 2 squared times 5. For 28, it's 2 times 2 times 7 equals 2 squared times 7. Now, to find the GCF, you're going to take the least power of each common prime factor. So you'll want to see which prime factors the 20, the 28, or any two numbers have in common. Well, the only factor they have in common is 2. That's the first step, the common prime factor. Now we take the least power. In this case, we take the prime factor with the smallest exponent. But in this case, both of them have an exponent of 2. Therefore, the greatest common factor is 2 squared, or 4, since the square is the least power of each common prime factor. That's how you do GCF. Prime factor, look for the common prime factors and take the smallest power of each of those numbers. Now let's look at the least common multiple. We have the same thing. Take the greatest power of each prime factor. So we're not looking for common factors. We are going to count for every prime factor. So we have a 2, we have a 5, and a 7. Our highest power for 2 is squared, so 2 squared times our 5 times our 7. So the least common multiple is the product of those three numbers, or 140. So once again, for least common multiple, you are taking the greatest power of each prime factor, and you will multiply them together. Example 3. Find the GCF and LCM of 100, 120, and 90. So let's start with the prime factorizations of each number. You can try these yourself. Why don't you try this yourself and restart the video when you're ready. Alright, so 100 is 2 times 2 times 5 times 5. Again, if you need to do the factor trees, go ahead and do those. I don't have the room to do it here, but you can figure out the answer. So 100 is 2 squared times 5 squared. For 120, if you break it down, you get 2 times 2 times 2 times 3 times 5, which is 2 cubed times 3 times 5. Finally, we have 90, which is 2 times 3 times 3 times 5, which is 2 times 3 squared times 5. Now, to find the greatest common factor, remember, we need to find the least power of each common prime factor. Does each number have a 2 in common? Yes, it does. What's the least power of all those 2's? It's this one, 2 to the first. So our GCF is going to have 1 2 in it. What about the 3's? Well, the 100 doesn't have a 3, so we can't use these 3's because it's not common to all three numbers. However, we do have a 5 prime factor, and the least power of 5 is found in both the 120 and the 90, which is the first power, or 5. We cannot use the 5 squared for greatest common factor because the 120 nor the 90 have a 5 squared. So we multiply the 2 times 5, the common prime factors. Both of those have the smallest exponent of 1, and so the GCF is 2 times 5, or 10. If we go to the least common multiple, we take the greatest power of each prime factor. So we have to make sure we have a 2, a 3, and a 5. And among those numbers, we take the highest power for each one. So we start with 2. Each prime factor, take the highest power. That's this one, 2 cubed. For 3, here it doesn't matter the 100 doesn't have a 3, because we're only making sure that each prime factor is accounted for. In this case, the greatest power for any 3 is this one. It's 3 squared. So far we have 2 cubed times 3 squared. Finally, we get to the 5. We see that the 100 has a 5 squared. So our greatest power of each prime factor is, for 2, it's cubed. For 3, it's squared. And for 5, it's squared. So our answer is 2 cubed times 3 squared times 5 squared, which multiplied together gives you 1800. So it might seem a little tedious and annoyingly simple. If you take the time to do it, it'll make a lot more sense. And these counting principles are going to help us a lot later on. We get into binomial expansion, some other topics during the second semester. Alright, now that we've mastered the GCF and LCM of numbers and integers, now we are going to add letters. And really, this makes it seem more complicated, but it's not really that much more difficult. The GCF of 2 or more monomials is the common factor that has the greatest degree and the greatest numerical coefficient. Remember what we talked about with degree when we looked at the exponents. It's the one with the highest exponent. The greatest numerical coefficient is just another way to find the GCF of the three coefficients or two coefficients of however many monomials there are. The LCM of two or more polynomials is the common multiple that has the least degree and the least positive numerical coefficient. So let's see how this works. Find the GCF and LCM of 8ax squared and 12a squared x. So the first step is to find the prime factors for the coefficients 8 and 12. So 8 is 2 times 2 times 2, or 2 cubed. 12 is 2 times 2 times 3, or 2 squared times 3. So to find the prime factors of coefficients, now we use the GCF of those two numbers. And if you remember how to find GCF, we take the smallest exponent with the common prime. In this case, both of them have a 2. 2 cubed and 2 squared. The smallest one is 2 squared, so the GCF is 2 squared. Now, we have to worry about the letters. To find the GCF, we had to find the power of each variable appearing in both monomials, then use the power with the least exponents. So, let's take a look at our original monomials. We have an 8ax squared and a 12a squared x. Let's ignore the numbers for a moment because we've already taken care of those. Both of them have at least one a. Both of them have at least one x as well. The smallest exponent for a is 1, which is here. Comparing the x to the smallest exponent for this x is here, also 1. So we have each variable appearing in both monomials, that's a and x, then the power with the least exponent, which is in this case is a to the first and x to the first. So between a and a squared, we're going to use a because a to the first is a smaller exponent. Between x squared and x, we're going to use x because x is the smallest exponent. Now to find the GCF of the whole thing, all you do is put the coefficient and all the variables together. So the GCF of these two monomials is 4ax. Again, all you do is find the prime factors of the coefficients, then find the GCF of those two numbers, and then for the letters, the variables, look for common variables appearing in all monomials, and then take the smallest power of each one. The LCM, we do the LCM for the coefficients first, and then we'll have the powers of the variable appearing in either monomial. Then for each one that appears, we use the power with the greatest exponent. So the LCM of 8 and 12, we take a 2 cubed because that is the highest power of 2, and 3 of the first, which is the highest power of 3. Multiply those together, the LCM is 24. Now, between the a and the a squared, again, they appear in either monomial. In this case, it happens to appear in both. We take the a squared because we want the power with the greatest exponent. Likewise, between x squared and x, we're going to choose x squared. So here, the least common multiple of 8ax squared and 12a squared x is 24a squared x squared. So make sure you remember, GCF, you're going to look for common primes and the smallest exponent. For LCM, you're going to be looking to make sure every variable appears in the answer and take the highest exponent that appears in any of the monomials. Finally, we have number 5, and we have 3 monomials. Find the GCF and LCM of 32x cubed y cubed, 120xy to the fourth, and 42x squared y cubed. I will give you a chance to do this. When you're ready to go, I would encourage you to resume the video. Alright, so we start off with the prime factorization of the 3 coefficients. We start out with the 32, and if you factor that, you would notice that it is 2 to the 5th power. For 120, if you factor that, you will get 2 cubed times 3 times 5. Finally, for the 42, you'll get 2 times 3 times 7. There are no exponents because all the prime numbers appear only once. So that takes care of the coefficients. Now, to find the GCF coefficients in common, the only coefficient they have, the only prime factor they have in common is 2. 32 only has 2, so no 3s, no 5s, no 7s. So the only factor common to all 3 is 2. From there, we take the 2 with the smallest exponent. So our greatest common factor is 2. For the variables, we take a look at the least exponents of variables appearing in all monomials. All 3 of them have an x variable. We take the smallest one. Here, x to the first power. That goes in our GCF. As we look at the y exponents, we have a y cubed, a y to the fourth, and the y cubed. The smallest power of y is cubed. We put that in there with the GCF as well. So you put all three of those elements together, and your GCF is 2xy cubed. Now the only step left to do is find the least common multiple. The least common multiple coefficients is 3360. How did we get that? You take the highest exponent of each factor that appears once, at least once. So the 2's, the highest power of 2 is 5, so that goes here. We have 3's, the highest power of 3 is just to the first. We put that in there. There's only one factor with a 5 prime factor, so that goes here, and a 7, of course, as well. So we have to multiply all these numbers together to get the LCM, which turns out to be 3,360. Now again, we do the same thing for the variables. And if you look at the x's, the highest degree of x is this one, x cubed. If we compare the y's, the highest degree of y is this one, y to the fourth. So the greatest exponents of all variables appearing in any monomial is x cubed, y to the fourth. So we put all three of those together, and our answer is 3,360 x cubed, y to the fourth. All right, that concludes section 4.4. I've been asked to give shout outs to some of my students. I thought about with the idea maybe of picking a random student by ID number, and if they say the phrase that pays, they get a late homework pass, or shout outs to names, but that's too much trouble, at least for this Sunday night. So we'll see you in class tomorrow. If you have any questions for Monday's lecture, save them, and we will go over them on Tuesday, and I will also give you some more examples of how to use the factor tree.